This research seminar is different. We have a small mini workshop this afternoon, starting from now, under the title "What are discovery and inventions? Lessons drawn from multiple discoveries and inventions in the 20th century physics." So we have this session, and then we move in after the break to 496, where we start at 6:15 with the second part. I will begin, before I will begin with things connected to the workshop itself. I will give all a minute.
It's going to be just 1 minute. I'm very happy and pleased that we are having our first Elkana Forum Workshop day. This is a new workshop that will be dedicated to finding conversations among scientists and among intellectuals and researchers in the humanities, trying to bring conversation about history and philosophy of disciplines and of the practices between practicing researchers. So this, I hope, will be the first of a glorious series of workshops where we can have these kinds of conversations. And I'm very pleased that this is our first one. And Shaul and Guy have organized this very quickly, this couple of weeks. But we are very happy to host this workshop, and I hope you all learn a lot from it. Thank you.
Thank you very much, Ori, and for the hospitality, and for Yossi is not here, but for the hospitality of the Institute and the department. I will say a few introductory words, and then I'll give the floor to Anastasiia and Guy. So, as the name of the workshop suggests, this workshop examines the question of what are discoveries and what are inventions. What do we require from a finding, a statement, an observation, or an artifact to consider it as a discovery or as an invention? The workshop has originated from this question as it emerged in a discussion between Guy Tetzroni and myself regarding discovery of the Aharonov-Bohm effect. Guy would say what it is, in his which he studies in the history of these studies. And I think it's an excellent intellectual reason for workshop that the question arises from naturally from the discussion. And I thank Guy and Anastasiia Lazutkina, who is the visitor from Wuppertal, and for Amichai Gal, the two of them joined us in short notice for this workshop. We'll attempt to focus the talk on the main issues of what are these discoveries and inventions, to which we also dedicate a panel at the end of the workshops, or the second part, and we also will try to keep time for discussion with the audience. The perspectives of multiples inventions and discoveries provides a vantage point to examine this question of what are discoveries and inventions. To decide whether two discoveries or inventions are similar enough to be considered as multiples, one needs to define the discovery. A task much more challenging than I would expect. Thus, this question highlights also other questions relevant to every discovery and invention. I would mention that with discovery that is usually also valid for inventions. Should discovery include all the ingredients later regarded as the discovery? And if not, which ingredient should it include? Do a theoretical prediction alone or an empirical observation alone constitute a discovery? What do discoverers need to realize in order to make a discovery rather than a mere theoretical or empirical observation? In other words, when does a finding become a discovery? These are the kinds of questions that we will examine this afternoon. The comparative and critical perspective of multiples show that we should look at the actual claims, ideas, and actions of the discoverers or inventors in order to evaluate their contribution rather than to stay in more general views. And I hope this will be more, this will be exemplified in the following talk. So we will begin with the talk we have been on the screen of Anastasiia Lazutkina from the University of Wuppertal. She is a PhD student at that university within a research collaboration of the Interdisciplinary Center for Science and Technology Studies. She works in history and philosophy and science with a focus on cosmology. And the title of her talk is Seeing the Cosmic Microwave Background Radiation Without Discovering It, Parallel Measurements Before 1965.
Thank you so much. Good afternoon, everyone. First of all, thank you for organizing the workshop and for inviting me here. It's a real pleasure to share with you the work I've been doing for my PhD in Germany. And thank you for attending my talk. So I'm a philosopher, and for me, scientific discovery connects to a larger question of matching the theory with the world. So as an inspiration kind of citation from philosophy of science, Howard Stein, I'll give you this citation. I suggest that the principal difficulty is not that of how to leave the theory outside the laboratory door, but that of how to get the laboratory inside the theory. And I hope that during my talk it will become clear what this means, how this affects what we mean by scientific discovery. So just very briefly about CMB, so cosmic microwave background radiation, the standard theory we have now about the universe is the Big Bang theory, which states that you have initial kind of beginning with a hot and dense state from which the universe evolves and expands, and during the expansion, the temperature cools down, and you have the different physical processes happening, the formation of the elements, and then at some moment you have the formation of the subatomic parts and the atoms, and then the galaxies, the stars, and etc. And then at some moment, the logic is like this, that if the universe began as a hot and dense, then early matter and light were tightly coupled, according to Big Bang. And then as the universe expanded, that radiation would cool down and redshift to the microwave part of the wavelength. And today, if that theory were to be the adequate description, we would see a cold afterglow or the radiation that we would be able to detect. And in fact, this did happen, as many of you might know. In 1964, Pezin and Wilson were working at the Bell Labs in the United States, and they were developing ultra-low noise spectral receivers for satellite and distance communications. Then they, so-called, the official history goes that they accidentally discovered the excess noise. They didn't know how to explain that. And then some cosmologists, so theoreticians, people together with the people they were working on building their own radiometer, Roland Wilkinson, interpreted as CMB. And so then, the 1978, they got the Nobel Prize, Kansas and Robert Wilson got the Nobel Prize for this discovery. So that's the official story. Now the question here is asked by several physicists already in the 70s and still now, is that, well, CMB was predicted to exist already in the 40s because this is when the Big Bang theory was largely developed. So why was it not detected earlier? Why was it not part of any kind of observational program? Why was no one looking for it? So Weinberg asked this in his famous book. And so what I will try to give you now is kind of the outline of my talk is that I will give you the predictions that were there in the 40s. And then the one who doesn't know this, but CMB was measured before 1960. But it was not interpreted. And then I'll turn to the philosophical part, which is what did turn the detection in 1964 into being interpretable as CMB and into being viewed as a discovery. So in 1940s, George Gamow was working a lot on the Big Bang nuclear synthesis, and together with his colleague Ralph Alpher and Hans Bethe, they wrote a paper about the abundance of elements. So basically, how do the primordial elements form in Big Bang nuclear synthesis using the nuclear physics of the early universe? So they were mostly focusing on hydrogen and helium and trying to explain sort of the Big Bang was the adequate description, that how would you have the formation. Then from that on, Ralph Alpher and Herman were working on more detailed predictions. So as I said, if you do state that nuclear synthesis and the Big Bang, then this would imply like a thermal radiation, and then there would be like a redshift to a microwave, and then there would be a relic radiation that survives now and comes to us we could detect. And they predict that. In 1948 paper, they predict that there would be a radiation left over about 5 Kelvin. And then later work on kind of things around it, sometimes change their predictions. Gamow is also later trying to, in the 50s, give different estimations of the temperature of the radiation, but they're not really thinking of how to measure it. So there's a story that Gamow was approached by a person working in the radio astronomy and asking, like, can I help you anyhow, like with your work? And Gamow said, I don't think so. I don't think there is anything interesting you could do. Like, so complete kind of disconnect between how to measure the radiation. In 1955, in the Soviet Union, in Baghdad and Leningrad, there were PhD students working on different technical problems related to calibrating radio equipment and measuring the radio waves. And he had his own antenna, which is not as accurate as Penn Wilson antenna, but it was a good antenna, like relative to the task. And it was also a point antenna, and he was detecting on that antenna the excessive noise, no matter where he pointed. And so he reported to his supervisors, he recorded the conferences, that he measured a few Kelvin excess that he couldn't explain otherwise. So he subtracted the absorption of antenna, he was looking at all the other possible explanations of what it is, but he couldn't find it out. So very similar to the logic of how Penzias and Wilson faced it years later. So he didn't know anything about CMB, neither did his supervisors, nor his colleagues, and he didn't interpret it. So there's one sociological explanation that back then Gamow already left the Soviet Union, and he was thought of as a traitor. So for many people, citing Gamow would be a kind of professional suicide, because you would be confirming something that the traitor has proposed. So that's one explanation. But then the problem with that explanation only is that it wasn't only this guy in the Soviet Union who detected it, but it was across the world. So even before Gamow, Alpher, and Herman were working on the predictions for the relic radiation, already in 1941, there was indirect evidence. So there was a guy, McKellar, who was measuring starlight passing through interstellar gas, and he inferred like background corresponding to around 2.3 Kelvin. There was a research in Canada, like showing around 5.5 Kelvin excess. Research in France, showing that the radio sky surveys left like around 3 plus minus 2 Kelvin. Research in Japan, where you had also, like after all the instrument calibration, you had several Kelvins left over. Research in Bell Labs itself before Penz and Wilson, so in 1961, showing excess of 2.3 and so on. So it's not just the ideology, and it's not just isolated case, but people just didn't know what are they measuring. And people who were working in cosmology didn't know how to measure what they were working. But then what changed, right? So you have these unexplained excesses. Sometimes people say, well, it might be atmosphere or so on. But in many cases, they just didn't provide any justification. So what changed then? This also accidental detection by Penz and Wilson, in the sense that they weren't cosmologists, they didn't know about Big Bang, they didn't know about CMB, but it got interpreted. And it did become a discovery of the century. So we do have some understanding of what empirical evidence is in philosophy of science. I think a really good approach is by Nora Boyd. So she claims that a result becomes evidentially usable when it is enriched with information about how it was produced. So calibration steps, corrections, background models, uncertainties and sensitivity, the assumptions. And of course, what happened at the Bell's Labs was a work of like very big care of the all those processes that were happening. So they were taking really great care of not making like bold claim without the backup. So they were checking all the possible contributions to the noise. And so the choices that they made, in this sense, they enriched the measurement with the workflow, with the metadata. So that made the structured data that they received into usable evidential constraint. So they had a clear expected noise budget. So they would have 2.3 Kelvin from atmosphere plus 1 from local contribution. They got excess, they subtracted, they got 3.4, and then months of eliminating sources. And I think the story many of you know about the pigeons, possibly droppings there in the antenna, trying to eliminate it as a possible source of the noise, but pigeons got killed. The noise didn't disappear. So, okay, so that explains at least the part that unlike the previous measurements, Penz and Wilson did really much more careful work, like many more stages of filtering of the data were done. But that doesn't explain how did it get connected to the field? How do you link the theory with the work? So there was another paper from Soviet Union in 1964 by Doroshkevich and Novikov. So they were familiar with the Big Bang theory, and they estimated cosmic radiation from galaxies over a wide frequency range and compared it to the data they had back then. And then they showed that, so this kind of black body cosmic microwave radiation would exceed galactic radiation in a particular frequency window. And they cited the Bell's Lab paper from 1961 and said that Bell's Lab is the place to detect CMB, that before the Kepler work is done. At the same time, in the early 60s, Robert Dicke and Jim Peebles were working in Princeton on different cosmological models. They didn't know about Gamow, but they did know about the possibility from inferring CMB from the Big Bang. So they kind of, the story is that Peebles kind of recalculated everything without knowing about Gamow's work. but what did they do in that paper that was different to the work that was done before? So they started a whole research program of building a radiometer, choosing different wavelengths, and estimating when and how you could measure non-CMB and CMB, and how to specify what is the atmospheric contribution, and how to measure it, how to tip the antenna, and so on. So while in the 40s, you did have the theory and you did have the predictions, but the way you thought of the problem was much more related to not knowing the exact instruments that you could use for measuring it. And if there were suggestions, those suggestions were usually like a bolometer that couldn't provide you reliable results. And so what changed in the 60s was not better theoretical work, was not more accurate predictions. It was actually the understanding of very, for a philosopher, trivial things like the error bars, the atmosphere, and then the noise contribution, and all kinds of possible pragmatics that wasn't there. And so that made, because Peebles and Dicke, they were making the radiometry before Pendleton detected CMB. And so when the detection happened, they were able to match this together. The model that they had, they were building within the framework to the structured data that Pendleton and Wilson provided. And so this brings me to the idea of general question in philosophy of science, that we usually think of scientific theories, that their ontology, what the theory is about, the meaning of the terms, has to do with the formal structures, with the solutions to the equations, with the different models, and then pragmatics and the roles of exact setup of experiments is somehow separate, not part of the content of the theory, not part of the experiment. And I think that this case shows that it's actually a big part of the epistemic content, because a theory is characterized by its epistemic content, the sum total of all forms of knowledge it embodies in all their aspects and relations to each other, as determined by our actual current state of knowledge about the world and about how to investigate it. So not just the formal parts of the theory, but actually more how we get to know how to connect those formal parts. And here, Eric Curiel, based on Stein and the idea of bringing the laboratory inside the theory, I think kind of provides the explanation for what it means to have the discovery of CMB, although he doesn't talk about it, but I take it to apply to this case. So he says that following Stein, I hold that a physical theory must schematize the observer within itself, that is, it must be able to represent the measurement process, at least in outline, using its own representational resources. So by schematizing the observer, I mean that in a model of experiment, to provide a representation of something like a measurement apparatus, even if only in the simplest and most abstract form that allows us to interpret the model as the model of the experiment or an observation. So the mechanism that mediates the theory and the world experience. And so I think that the discovery in this case was that when Penn and Wilson provided more or less structured data here, due to the careful work they did, Dicke and Peebles were able to provide this schematization within the same framework of the microwave and radiometry analysis, providing a special window of where to look for CMB, where you can do the right reflection. And so this allowed this matching to happen of your individual model. Okay, there is solutions to your equations. Of course, the formal parts are very important, but this connected things. So, and this, I think, brings me to the idea that discovery requires both the enriching evidence process, of course, plays a very important role. But I think that the ability to schematize the observer within their representational resources of your theory, to be able to link that this is what happened with C and B, and this is what Stein means by the difficulty of getting the laboratory inside the tolerance theory.
Thank you very much. We have also some time for questions, and please. Abdullah.
I was wondering if you can connect it to some advances in practical radio design that results from expanding the radio field. Because this very design for radio is not really now for magic. The ability to decide that certain noise source is inexplicable by current physics is anything but trivial. So I was wondering if you can expand on what happened during the 40s and 50s that allowed the researchers to be so confident that the very slight difference they see means that they are observing a natural phenomenon, motion, one that rectifies everything. They should be not extremely confident in their results.
Yes.
And in the field they want to allow it to remember.
Yes, so I think this happened only by the 60s that this confidence was built up. But in the 50s, you already knew quite a lot because you had all the radio technology left over from the war, and so it entered science, right? And this is what started to happen. And you could subtract things. So the thing is that you knew at least enough to subtract the atmosphere, to subtract the noise of the antenna itself. So the practical work related to the subtraction of like external reasons was developing on its own. No one interpreted it in the 50s as a phenomenon that relates to cosmology, right? So yeah, of course, and they couldn't do that. They couldn't do it, but at least they were saying that you can't just say that this is the measurement mistakes.
What was the theory that allowed them to be so confident? What was like detection, whatever?
Yeah, I don't. The theory that provides confidence. Yeah. Maybe. Yeah. In general, I don't agree. That's not. Yeah.
Thank you. It was very interesting case study and then the presentation. But what I was wondering about is how general is the picture that you're presenting, or would you generalize these conclusions about putting the laboratory into the theory, which I'm not sure I fully understand. So when we think about discoveries in other areas of science, maybe you can help me see how this generalizes, because if I think about discoveries in, say, the history of biology or genetics and so on, I'm not sure how I would map this. And part of cleaning the data and so on, that's very easy to transfer this idea. But the second part, I'm a bit of a loss at. So if you can.
Yeah, so my discussion applies, at least to my knowledge, physics. I'm mostly like the discoveries related to theoretical physics and their own. I myself am wondering how much it could apply to biology. But that is an open question. It does apply. This thing applies to gravitational waves, which is again physics. It does apply to like there is work by Michael Kufara on quantum mechanics and application of that quantum mechanics and physics. There's work that does this with the clusters, I think, but all of this has to do with physics. I guess that it does have application to biology just because I think that there are similarities there one could find. But this is just a guess. How would you schematize the certain kind of, how would you schematize the observer within a certain biological theory so that you could recognize data as something you need to structure? I don't know how one would approach the data and structure it without having a certain, like, as a confirmation of your theory, without having that schematization. But that would require a work with a particular case studies.
No, that's what I saw you and the list, okay? Tony?
I'm curious about the notion of bringing the laboratory into theory.
Yes.
And what exactly does that look like? It reminds me of if you read the Newton's optics, who develops all of these propositions and then he draws various kinds of experiments that he's done, but mostly with prisms. And then he would draw a very complicated apparatus, and at the end he would draw this little eye that would represent the observer. Okay, so that's a very, I don't know if it's very helpful in schematizing the laboratory and bringing the observer into the theory. But how does one represent the observer within a formal theory?
So the thing is that that's exactly the point about this division, that the theory is the formal like content. So if you reject that division and you say that the theory is not just formal parts, but it is all the like, well, visualization, all the things you have to say about how would you particularly use those formal structures in their application and possible testing. So you're not bringing the observer inside the formal structures. You are you're using. So sometimes the word that can be used here is like you're using the general framework of the same language that you could use, like of the same terms that you could use for interpreting the formal structures and for giving a model of the experiment. So this has to be there has to be a link, it has to be shared. So in that sense, bringing the observer inside is doing what I think, well, in this case was done by Dicke, is that saying that if there is C and D, then we need to build radiometers like this and this and this, look at that wavelength, subtract that and that and that. This didn't bring the, it didn't change the formal parts. Actually, they were working on even a different cosmological model. So that didn't even matter that much because the shared framework of the general idea of cosmology and how to connect it with the terms that are used in the model of the experiment, that's what allowed you to connect the experiment to the theory. I think I'll say something like that. But Newton did use that, and indeed, even with the cases, but with the planets, there is a particular part I can give you later the reference where he talks about this, how exactly the deviations would be on the movements and how would you measure those deviations? How, providing the actual experiment, right, within the certain framework. Something like that.
Thanks. I have two questions and maybe also one. The first one is right. So you mentioned all of these measurements of noise that predated the Penzias simulation, And I'm wondering if they were, if you know, if they were all giving the noise in like black body temperature, or is it something we are doing at the insight to compare it to the 3.7 that you all know? Because if, I mean, if some, I know, I don't know much about it still, but if somebody is measuring some noise, is it, would they automatically translate it to black body temperature?
No, but the results that I showed, these were later, of course, like in the retrospect, like rechecked and confirmed that this seems to be the.
But they were giving it anyway.
Well, back then when they were writing, but then they were saying, well, maybe there is something else that's responsible for that. Again, like they were just like maybe the atmosphere, maybe something like just excessive noise. I mean, yeah. So or just
the question, I think,
yeah.
whether did they give that in temperature or did they give that in energy of?
No, they gave it in temperature, so it's not.
They did give it the temperature, what you
Yes.
did, or,
Yes,
and you know why?
in Kellogg's. They did.
Yeah.
Yeah, because, well, so for example, the Soviet guy, he was measuring like the absolute temperature of the skies, so he was pointing and measuring it, and that was what, +7 plus -3 current in everything. So, wasn't bad.
This may be a question of pure ignorance, but going back to biology for a second, isn't this case study somewhat similar to what happened with the discovery of DNA with Watson and Crick, where they have data from another scientist which they correctly interpreted? I'm sorry, I know it's not correctly.
Oh, but it's very interesting.
Just around.
I try to understand, like Ori, what it means to bring the lab into the theory. Since I don't understand, I cannot tell you if this is the same case. It seems to me that this very idea, which I try to get you to explain, because I'm still at a loss at, goes against any basic understanding of division of labor in science, right? So I don't think theorizing the observer is something most scientists, like say Watson and Crick, were trying to do. They were trying to interpret data of various kinds, and that language is easier for me to understand, right? Which is why I was asking, what exactly does it mean to put the laboratory into the theory? Because again, I was trying to understand. I'm not sure I understand what this means.
Perhaps something from turning observations into evidence.
Well,
In the
yeah,
sense.
yeah, so the way you.
That's the big question here, right?
Yeah, how to do it.
I think maybe, so I think we should differentiate between the process that leads you to the discovery and the process where you know that you've seen something, but you don't understand it yet, or trying to interpret it. So it seems like bringing the laboratory into the theory is the part where you search for looking for something. You don't even know, not at the stage of interpreting.
Well, it will depend. I think it's not a universal thing, because of course discoveries can happen in different ways. And sometimes you look for things for very long and you just don't know like when you will find it, and sometimes. But I think in both cases, this schematization would be like the mechanism that would allow you to identify things. So I don't know if it helps. But think of this like this. There's no schematization of observant quantum gravity. So the extended content of quantum gravity is very, very. But there is a very clear understanding from like general theories of galactic dynamics and astronomy what galaxies are. You can schematize them pretty well. So the idea, like, is representational capabilities of different models, the theories within the framework of how can they be matched to data? Like what allows you to say that the raw data that you get, you could structure it into something that matches the model. What is this that allows you?
Do you think that the agreement between the results of the measurements and the predictions of the theory for the existence of the relic radiation is important for making it discovered? And if it is important, what would you say regarding dark matter or dark energy?
I'm a long person, but no, that's a joke. So let me start with the first question. So the predictions, they were very important, but at the moment of, at least the official history goes like this, that at the moment of the discovery, no one knew about the predictions from the 40s, right? So Peebles and Dicke, they re-derived the whole thing. And the kind of the accuracy of predictions is not as important. I think that it is very important for many other things, but for that particular story, what was more important is the realization of where to look for data. So where to look for the regulation. The predictions became important much later when you started to develop different kind of approaches to how to study CMB, how to study overall the universe and structure formation and so on. Now, so that's the first part, right? The question about the role of predictions for this case. For about the question of dark matter, what is the question about predictions here?
I was wondering if you think that the agreement between the results of the measurement,
yes,
and the predictions of the theory is important for making that result a discovery, and if it's important or if it's not, because in the case of dark matter or dark energy, there is I'm not sure if there is agreement or the agreement came afterward. As a result of rebuilding the theory to fit the
yes.
So is that a discovery?
Oh no, absolutely. The dark matter is not a discovery. This is not a scientific discovery as of yet. Sorry, and much less dark energy. So that's for sure outside of any term. I mean, yeah, I wouldn't use for many different reasons. In case of CMB, of course, when you have the matching, when you do the matching, of course you compare the predictions and the actual measurements. Of course this happens. And I don't know how to not make it not to make it a non-important thing. It is important. But I think that this plays the role only once you identify that. What do you actually you are bringing the detectability regime. So I don't know the term, the regime in which you could potentially detect something. You're defining the applicability, and then you're doing the prediction comparison. So the first step is before you compare the accuracy of prediction. So it does play a huge role, but I think here it plays maybe temporally later role.
Oh, very cool. If I may contribute to
Yes.
there used to be a professor here in physics, Jonas Alster. He once told me that his entire career was based on the idea that other things usually produce papers that combine theories and measurements, which are poorly measured. So what he does, so this is the only thing I do, is to take the setup and produce it with 10 times better accuracy and measure the difference between that in the theory, because there is always something, and then you can plot it. So, I think I demand something like that.
what this,
I know what we're doing.
yeah, I think,
So,
yeah, I think this is an interesting example. Yeah, thank you.
So thank you, Anastasiia. Moving to the second talk by Guy Fitzroy. Guy is a philosopher of science based in the Department of Natural Sciences at the Open University of Israel. His visual studies the epistemology of theoretical practice, chiefly in the context of contemporary physics. Among other projects, he currently studies the conceptual shifts in quantum mechanics from the 1950s and the 1980s. It's talking about excluded fields and missed potential discoveries and oversights in the Aharonov effects in part of research.
Thank you, Shaul. We're really thankful to Shaul and Ori and the Institute for organizing this thing at a really short notice. So basically, this original research was not about multiple discoveries. But then about a month ago, I guess I talked at the Ben-Gurion University at the Israeli Society Conference, and Shaul asked me about this aspect. So basically, this talk is sort of hybrid between the original question that I had in mind, so say what it is, and that I will try more to give more focus to this new aspect of multiple discoveries. And also, another disclaimer is that I'm much more a philosopher than I am a historian, and this work is as far into history as I got so far, even though I'm rather you will be getting a bit more. But I mean, I don't have as a philosopher an opinion on this question of what is discovery, and it's part of what I'm trying to find out in this workshop. But I mean, I think that this case study is really interesting from this respect. Okay, so this was the very general introduction, and maybe to tell you what I'm going to talk about, I first need to tell you what the Aharonov bomb effect is. So in 1959, Yakir Aharonov and David Bohm were both. Yakir was a PhD student at the University of Bristol. Bohm was a supervisor. We'll tell more about it later. So they published this paper, significance of the electromagnetic potentials in quantum theory, in physical review, and they're not in the following. So let's imagine that we have sort of a double slit experiment in quantum mechanics. So we have like an electron beam, and maybe you can think of it as a beam of one electron at a time, or it doesn't really matter. And B and C are like the two slits from which the electron can pass. And then here we have interference pattern, like in any double slit experiment. And then they said, okay, what if we put here in the middle a solenoid, which is source of the magnetic field? But the solenoid is ideal, it's long and infinite, so the magnetic field is confined within it. And we even, just to be on the safe side, put here a metal foil, such that we are sure that there is no way that the wave function of the electron gets here into the solenoid. There is no overlap between the electromagnetic field and the wave function. And then what you realize is that nevertheless, even though there is no local interaction between the wave function representing the electron in this interference experiment and the magnetic field, nevertheless, quantum mechanics predicts that there will be a change in the interference rate. And they one way to interpret it, which is their suggestion, is well, maybe the field is not the main thing, but the potential. It was considered something completely mathematical auxiliary, right? Potential is something that we use if we have like conductors, and we need to calculate the boundary conditions or whatever. But the field was taken to be the real thing, but then, well, if we don't want it to have like a non-local effect of the field of the particles, then the potentials are the significant element. And then when they published this paper, it made great impact. So first of all, people began to do experiments, and then it took less than 3 years for the first experiment by chambers. And then for the coming years, there was a group in the United States, in superconductors, and a group in Germany, and other groups, and then later, of course, the group in Japan. We're doing the experiment. And then there were also debates whether this effect exists at all, or is it just a mathematical artifact. And then there were many debates over the interpretation. And when I'm saying debates over the interpretation, it's a little different than what we think about interpretation of debates in quantum theory, because most of the people who were taking part in these debates are actually quantum field theorists, like Weiss, De Witt, and Dimension, that are not usually taking part in the interpretation debates. So here you can see a 1962 conference. It's before Bell's inequality, so it was a conference on the foundation of quantum mechanics. Boris Podolsky here organized it at his university in Ohio, in Cincinnati. And in the front row, you can see Eugene Wigner, Nathan Rosen, Paul Dirac, Podolsky. This is a very young Yakir Aharonov, not yet 30, and this is Vedel Turit. Everything is also here. So this discovery put Yakir at the front line with all of these notable physicists and very other interesting persons, and the effect was one of the main things that were discussed there. And then later on in the 80s, there was the Nomura experiment. So here you can see Yakir Aharonov with Yakir Nomura, who conducted the experiment, which is considered like the final verification, the good accuracy verification of the effect. And this is a novel at Chen Yang, when they were meeting in the first symposium of quantum foundation in light technology in Japan. And so basically, the point to take from this is that it made lots of noise. It was like something revolutionary in a way. It was conceived as such by the community, even though small community, quite immediately. And recently, I published this oral history interview with Yakir Aharonov, where he gives his perspective over how the discovery was made and the debates about it, the interpretation of debates, and it's already published, you can find it. But what I would like to talk about here is what happened here. And then, so, and the question is, well, basically, the Aharonov effect is just to take the Schrödinger equation as it is, and you apply it. There is no new theory. It's the same quantum theory from the mid-20s. Then why was it discovered so late? And when I was talking with Yakir Aharonov about this question, he told me that I was not the first to ask it. So apparently Richard Feynman in his lectures on physics that were given in the early 60s, so not very many years after the Aharonov paper, is saying, it seems strange in retrospect that no one thought of discussing this experiment until 1959 when Bob Aharonov made the whole question crystal clear. It's interesting that something like this can be around for 30 years, but because of certain prejudices of what is and is not significant, continues to be ignored. So this was the question that I was asking, and along the way I realized that this question by Feynman is really similar to the big question that historians of quantum mechanics are asking today about what is now called the second quantum revolution. So this is basically, which is related to Bell inequalities and the conceptualization of entanglement during between the 60s and the 80s, which is related also to the supposed revolution in quantum computing, which is coming. So that was the question that I had in mind. But I mean, I'll try not to talk too much about this aspect and to try to talk more from this point about the multiple inventions. So what we see here is that we find a series of what I would argue are almost discoveries, and then maybe even an actual discovery, which will be try to give me some focus and compare it. So let me start with the theoretical thread of something like almost discoveries. And I wasn't planning to talk a lot about it. I think I thought to go really fast about it. Right? Actually, in this 1918 paper, there is something that's more related to the talk by Anastasiia. So the story begins before quantum mechanics. And in general relativity, if you take like a vector, any vector, you parallel transport it like on the curved surface, it gets back to its original position, and you realize that it rotated a little bit. This is related to the notion of geometrical curvature. So Hermann Weyl in 1918, just 3 years after general relativity, he tries to generalize and he suggests the first unified fields theory, which basically says, well, what if also with the magnitude of the vector would change? Then apparently, in a contemporary language of mathematics, we would say that we need to introduce a scale connection. And apparently this scale connection has exactly the degrees of freedom which are related to the electromagnetic four-vector potential. So basically, what Weyl is realizing is in a way very close to the Aharonov-Bohm effect, even though before quantum mechanics, which is that the content of classical electromagnetism could be expressed using what mathematicians or sometimes theoretical physicists call today holonomies, which is the thing that changes when you go around the closed loop and get back to the original position. What I wanted to say now also about it is that this was immediately attacked by Einstein. He said, well, if your theory were true, then if you take two hydrogen atoms, separate them, they would come back to the same place, and then they would have different spectra. And Weyl said, well, no, there are different ways. It's not really immediate to coordinate the theory with the measurements in this way. It's a mathematical theory, and there is more than one way to coordinate it. And it's really, I think it's very good. So this notion of coordination, you have like a formal theory, and how will it relate to measurement is really close in a way to what Curiel was talking about. Anyway, I will not say much about the rest of these papers, only the Schrödinger before the quantum theory notice that there is something peculiar here that is different, that is could explain many experiments, and even maybe we should take it as a complex number, this factor. And then later on, Fritz London realized that after Schrödinger quantum theory, realized that it just appears there, and then this integral is really the Aharonov-Bohm integral, even though it's now connected to a length scale. And then Dirac, in his monopole theory, also pretty much identifies that the change in a phase around the closed curve should be the same for all wave functions. This change was then interpreted by the equation, which was very similar to Aharonov-Bohm equation of the phase calculation, equal to the total flux, which is basically the equation that Aharonov-Bohm have in there. And he says, well, there is nothing new about it. Weyl already, this is what Dirac is saying, Weyl already noted it in his 1918 paper. So the one thing that none of them notices is that they don't need the local interaction to have this influence. And this is the essence of the effect, right? Okay. So what I would like to take from this theoretical thread of very famous and notable physicists almost discovering the effect, in my opinion, is that discovering the effect is not the same as taking the dependencies among the theoretical and measurable quantities, because they know how that the theory is related to observations, all possible observations, but they still did not see like the effect. Even though that if they would try to calculate this equation, they could have calculated it. Okay, now I would like to talk about a different thread, which maybe has more like of an actual discovery. And it's based in part by this paper by Ehrenberg and Stein, which I will talk about, and also about the paper by David Heine, who was later in the 80s and 90s collaborator of David Bohm. And he knows that somebody in Leipzig called Walter Franz noted that the phase difference depends on the flux, same as Dirac. But he only noted in writing that it does not require direct interaction in 65 after Aharonov-Bohm detection. So it's not clear whether he realized that there is this effect before Aharonov-Bohm or not. And the evidence here is like, it's not like an actual paper, it's more like suggested talks that he gave and lecture notes, so it's not so clear if he saw that there is an effect here. And then Ehrenberg and Stein, which is the thing that I would like to elaborate here, because this is like where the part of the multiple discoveries comes into play. And so they publish this paper, the refractive index in electron optics and the principle of dynamics. They publish it in a proceeding of the Physical Society, which is a good journal, very good physics journal, but not the top journal, and in 1949. And then they're suggesting basically this. So this setup is almost exactly or as our Van diagram that I showed before. Right? You have here the interference region, you have here the split, and then this so-called lens is whatever is causing the two beams to come together again. So it's very much the same. And here we have in this rectangle the confined electric field, or sorry, magnetic field. They only talk about magnetic field. Even though there is also an electric effect, which they don't notice. And then they're saying in their paper the following sentence: one might therefore expect wave optical phenomena to arise which are due to the presence of the magnetic field, but not due to the magnetic field itself, i.e., which arise whilst the rays are in field-free regions only. So it seems like they are discovering the effect, right? It's 1949, and they're first of all, they're suggesting the same experiment. And then also in this highlighted sentence, they're also basically saying the important point. So how are they discovering the effect? So this is like the discussion. Now, there are a lot of debates, some debates about it in physics, which are all related to questions of the credit and the prizes, and how it should be called the effect. Now, I study the epistemology of science and try to look at scientific progress, and I'm not very much interested in the question of credit. So I think it's sort of a red herring. But there are, it is a debatable issue. Now, why do I think there is a place for questions? So let's zoom out a little bit. This is the figure 3 that I showed before, which was shown together with figure 1 and figure 2 in their paper. And what we could see here is that figure 1 and figure 2 relate to an experiment in which the planar electron wave does go through the field. The circle here is the area of the field. So here there is a direct interaction with the field. And this is the plot that I showed before, but then which is part of the last paragraphs of the paper. But you see that in this quote, it does not even get its own paragraph. That's something that they say, and then the last paragraph of the paper, they can conclude it with the following point. It is curious that equation 50, which is the same equation more or less as in Elkana calculating the phase difference, associates a phenomenon observable at least in principle with a flux. One expects a change of flux, but not a steady flux to have observable effects. Now, if you don't know much about physics, the important point is that it is true, it is maybe somewhat peculiar, but this is not that peculiar point. Effect. So in a way, they see the effect, they state it, and they don't present it as something significant. And if you look at the abstract of the paper, so this is the abstract, and if I wouldn't have highlighted this last stance, so we have some theoretical framework to examine the contingency of the vector potential, contingency or something similar. And then the results are applied to a number of questions, such as differential equations, the trajectory, the zero symmetric field, and the inference pattern for that. And they're not, so it's applied to this question, they're not even stating the answer. So in a way, they're not seeing how important it is. And this is why I think it's a very interesting question for this question of what is discovered in the experiment. So to conclude about Ehrenberg and Stein, they describe the same experiment. They seem to not fully grasp its significance, and then between 1949 and 1959, it only gets cited in this paper 3 times. So before I said that discovering the effect is not the same as taking the theoretical dependencies, now here I had the original slide that said discovering the effect is not the same as suggesting the experiment, which I think it's obviously true. They only suggested the experiment. You wouldn't accept it if you discover the effect, but Shaul pointed to me correctly that they did more than that. I mean, and then the question that I don't have a good answer to would be, I mean, how far do we need to go? Do we need, in order to make the discovery, should they suggest the experiment and also explicate its significance, also presents its significance in the context of some questions that the community is already interested in? Should they convince the community that it is significant? And now in this case, Ehrenberg was a professor in Wuppertal College, so he was in a good and certain and respected place, and later on he became the head of experimental physics there. So I don't think it's like it's not like the case of Sekar coming from India and having to convince the community from the outside. They're from the inside, but in a more experimental community. And maybe also the times are different. There's not that much interest in foundations. Okay, how much time do I have? Okay, so try to go quick and to say what was different in the case of Aharonov and Bohm. So this is David Bohm in the 50s, and this is from the early 50s, and due to McCarthy persecution, he famously has to, but he doesn't have to, but Oppenheimer tells him he's better leave the country. He's expelled from Princeton, he goes to Brazil, doesn't find studies in Brazil, he comes to the Technion in Israel, which was a very small place, one prominent physicist, Nathan Rosen, and some PhD students, or maybe undergraduate students, not me, actually. And he comes there, and this is the Technion, the old building of the Technion. And there he meets Yehiel Aharonov. Later on, he's going to Bristol, and Yehiel Aharonov and another PhD student go with him. And this is where they make the discoveries, and this is how Yehiel described about a year ago the way he discovered the effect. So basically, it's more like the discovery came first from Yehiel. Bohm also gives the credit to Yehiel, and these are all interviews, and there's no questions about it. And he's saying the following thing already at the Technion, and was excited about the work of Felix Bloch, who found out that when you have a periodic potential there must be a gap in energy. This gap is the idea behind the explanation of all the beautiful phenomena of crystals. And it's basic idea that led to transistors. So before the almost discovery that I showed, they came from theoretical physics, very theoretical physics. While Dirac theory is looking at semiconductors, something very practical, very down to earth. My thought was, what if instead of potential that is periodic as a function of position, we consider the potential that is periodic as a function of time variable. In this case, you replace position by time, so you should replace momentum by energy, the energy by momentum, then maybe there would be a gap in momentum, but we don't get a gap in momentum, we don't get it, you only get like a phase that doesn't do anything. But then you realize that, okay, what if this phase, the global phase that doesn't do anything, what if we separate the two wave packets, we have this interference pattern, and we apply a time-dependent potential differently for each of them. This is the first figure for the paper. So here we have like electric potential, time-dependent electric potential, which is different from the time-dependent electric potential for the algorithm. Then we could think about interference that will lead to an observable result. So I thought about the idea of going too far with it, etc. Okay, so this is basically the the idea. So let me skip this for now, and we'll briefly come back to this later. And so how was the paper unique? So first of all, they presented both the electric and the magnetic effect, not the magnetic effect only. Ehrenberg and Stein did not see the electric effect at all. And Dicke is saying that later he met Ehrenberg in Birkbeck, and Baum was later situated in Birkbeck. And Ehrenberg did not believe that there would be any electric effect at all. They did the exact calculation of the wave function scattering. So basically, it's a very analytic calculation of the planar wave, and then infinitesimal flux, and how the scattering be. And then I think that the most important thing is that they present their experiment in the style of Einstein, Podolsky, and Rosenthal experiment. The paper is very much structured in the same way, in my opinion. Here is a thought experiment. What we could measure. What does it tell us about locality? What does it tell us about reality? And these are probably the elements that make it very influential. So first of all, what could in principle be measured in this thought experiment? And what does it tell us about foundations, about ecology, about locality? And so what were the reactions? So Feynman, and before his lectures in physics, he tabled David Bohm, which he knew personally. How beautiful! How come I never thought about it myself? Which is the question that makes a lot of sense. If you think that Feynman wasn't the only person to think about foundations of electromagnetism, classical electromagnetism, together with Wheeler, and the path integral. And then Niels Bohr said the effect can't exist. He had an argument for that, but it's all second or third hand verbal, what we know about it. Later on, he changed his mind. Later on, he came up with Ige Peterson, who was very close to Bohr, and we learned about it maybe from him, and also from another child, never mind. And then there were interpretation debate. The fact is this, but we should understand it through quantum field theories and local operators. The local operators or holonomies like Wu and Yang in 1965. So if we go back to Feynman's question, there was some prejudice that prevented physicists from finding out the effect. What was this prejudice? I'll try to answer this question, to speculate what would it be. And then first of all, if you look at the first half of the 20th century, there is no foundational discourse on classical electromagnetism. Not only in quantum theory, which is a different story, but it's about classical electromagnetism. Do we need to think more about the potentials, more about the fields? People were not interested in this. They were doing 3D, right? The discourse was very theoretical, not understanding and thought beyond the formalism. So basically, people at the time were struggling with the question of renormalizability. They were trying to write down the theory. And maybe there was this feeling that once we have the theory, we know everything. We don't need to try to find out what does the theory mean. We don't need to think of thought experiments that will tell us what does the theory mean. We need to write down the theory, overcome the infinities that come in the way, and when we have the theory, we have everything infinite. And then there is this issue with Bohm, which I think is very much related to the question of historians about the second quantum revolution. I have a lot to say about it. But I think that there was this question that you shouldn't ask this question of what is observable in principle, because I think that's part of what people call the Copenhagen orthodoxy, which is something that is very debatable, wasn't such an orthodoxy. I think that one implicit assumption was that at the observable level, everything becomes classical again. You have the classical correspondence, you have complementarity between two classical worlds. So at the observable level, everything will become sort of classical. The world is very strange, it's very different from the classical world, but this is sort of hidden from us beyond some epistemic constraints. So, and then the question is, what helped to overcome these prejudices? So first of all, there is the interpretation of discourse bridging theory and experiment. I showed you how it was almost discovered from the theoretical perspective, how it was discovered and ignored from the experimental perspective. The discovery, which is very much related to the talk of Anastasiia, is exactly about this bridging of theory and experiment. And then there are potential experimental possibilities. What could we measure in principle? And then there was better theoretical understanding of quantum phenomena that resulted from non-foundational research in semiconductors, in superconductors, and in plasma physics that was actually doing some work here, even though it wasn't foundational. Bob worked a lot about it. You hear describe himself as thinking about it when he was going to the effect. So these non-foundational aspects were doing some work in the way to the foundation. So this is basically